Okay, so the subject is approximate verification. So here we are mostly in a computer science area. So verification means something relatively standard. Okay, now I recall, now approximate is not standard. Okay, you have many possible definition of approximation, and we'll see essentially different models of approximation, and we'll compare them together. Okay, so now for computer scientists, essentially for theoreticians, verification usually means, and it's usually associated to the complexity class NP. Okay. Why? Because essentially you're given a problem, okay, and then proving the solution of a problem essentially requires guessing something, but whatever you guess can be verified quickly. Okay, so usually people associate to NP the class of problems that can be efficiently verified. Which can be, and efficiently, of course, means polynomial time computable. Okay, so typical, when I say a problem, what is it? Well, typically, you're given some finite object, typically a finite graph, for example, or finite word, or finite tree. Let's suppose, so what is a finite graph for us? Well, usually I write it like this, with an index for the size of the graph. So it's a domain with n element, and it's a binary relation on the domain. So essentially, okay, so you have a domain. You can think of the element of the domain as 1, 2, up to n. And then you have a binary relation on this domain. This is what most people call a finite graph. And now suppose I give you two of those. Okay, so I give them, so the input here would be a graph G1, and of course they will have the same number of points. And I ask you, well, are they isomorphic? So this is the question I'm asking. Okay. Well, let's put the one here. And of course, what does it mean? It means that you can find a mapping from the domain of G1 to the domain of G2, such that if you have two edges in G1, the image of that edge will be also an edge in G2, and conversely. Okay? It's clear? So it's isomorphic if there exists actually a permutation pi such that if you can write G2 is pi of G1. Okay, this is a notation which means, the isomorphic, you take G1 and you look at edges as taking the image along pi. Okay? Now if you ask this question to somebody, to a prover, usually we think of a prover. Okay, so you have a prover, the prover is given the input, and if you want to convince that he knows how to decide this problem, you expect him to give you pi. Okay, and you give pi to a verifier, and the verifier works in polynomial time, always. Okay, verifier is always poly bounded. Okay, so if you give me some permutation, well, first of all, you have to think of what is a permutation, but think of a permutation as essentially, for example, if you're on a domain of 1, 2, 3, 4, 5, for example, 1, 4, 5, 2, 3. Okay, so that would be the permutation that decides how do you map the elements. Okay, so pi gives you the image of 1 is 1, the image of 2 is 4, the image of 3 is 5, the image of 4 is 2, the image of 5 is 3. Okay, so that's the representation of pi. Okay, now if you give me this, well, how long does it take me to verify if it's correct? Well, what am I going to do is take all the edges of G1, take the image by pi, and verify if it's in G2, and conversely. Okay? Now, the question is, okay, can you, so the fundamental question here is, can we find this permutation in polynomial time? Okay, that's a very important question, and nobody knows how to answer this question. Okay? But then, you can also think of a slightly different problem, where you're not asking if the graphs are isomorphic, but you're asking the opposite. If the graphs are non-isomorphic. Okay? So tell me if the graphs are not isomorphic. All right? So if you keep this schema, if you view a prover, try to convince me that the two graphs are non-isomorphic, what should he send? Okay? And usually what he sends is called a certificate or a proof. Okay? And that's how the NP class was built, essentially, because it's a class of problem for which there is a certificate that you can verify in polynomial time. Okay? But now, what should the certificate, is there a certificate to prove that G1 is not isomorphic to G2? Okay? And of course, by certificate, people think of something which is of polynomial length. Okay? So certificate here. So here we have these synonyms where you think of certificate. Often it's associated to a proof. Okay, and this has to be of polynomial size. Okay? So, first of all, whether there is a certificate, a polynomial size certificate to decide this, nobody knows. Okay? But if you think of it, intuitively, how could I convince you that two graphs are not isomorphic? Well, the stupid method is to enumerate all the pi's. I enumerate all possible permutations. So I have factorial n possibilities. And for each of these permutations, I try to show that this is not true. An edge that doesn't match. Okay, so what is the size of the certificate? The enumeration of all the pi's. It is an exponential size, right? Factorial n is like 2 to the n. So it's not a polynomial size. Okay? And could it be possible that, we find a short certificate? Well, at this point, it's very much an open question. And of course, I think nobody believes there is such a short certificate. Okay? Now, what we're going to see in a minute is if I approximate in some sense, I will have a short certificate. Okay, so the first notion of approximation, which I'll define in a minute, is that I'll see by changing the classical schema here. Okay, I will have a very nice, very simple, small certificate. Okay, so that's the first example we'll run through, but this is a typical, so it's a basic example to introduce the complexity world as a class P. So you look at the class of problem like this. You usually view some kind of hierarchy. So you have the NP class. And then you have the complement of an NP class, which is co-NP. So a problem is in co-NP if its complement is in NP. So if this problem isomorphism is in NP, then this problem is a complement because I switch 0 and 1 if you want, so it's in co-NP. Okay, so usually this is called non-isomorphism. So non-isomorphism is a problem here. Okay, isomorphism is a problem here. Okay, and then you have a whole bunch of hierarchy here, which is called the polynomial hierarchy. And then about the polynomial hierarchy, you have a problem that can be solved in polynomial space. Okay, and in this area in between, there is another interesting class called P to the sharp P. Okay, so I'll introduce this in a minute. Maybe you've seen this already. And now we'll switch to a second example, simple example. Okay, so what is our second example? You see, you can view this binary relation as a matrix. Okay, and usually that's what people call the adjacency matrix of a graph. Okay, so let's take a set of graph matrices. Okay, and they can be Boolean. So in case of a graph, it's a Boolean matrix. So think of a, now I call it A is a n by n matrix. Okay, n matrix. And let's look at a couple of interesting problems, typical linear algebra type problems, but where we're going to go higher in complexity and sort of give a more elaborate example of this situation here. So maybe you all know what the determinant of the matrix is. Okay. Okay, usually related to the computation of the inverse of the matrix. Okay, but maybe, I don't know if you know this function, which is also interesting, which is the permanent of A. So if you haven't heard about the permanent, it's like the determinant, except, you know, the determinant, you have this -1 to the epsilon of the permutation, signature of the permutation. Well, replace all the -1 to something by +1. Okay, and you get a permanent. So you can also write it as a sum over all permutation of the product of AI pi sub I over I going from 1 to n. Okay, so you do the sum of all permutation of the AI pi sub I, you multiply. If you were doing the determinant here, you would add a -1 to the signature of pi. Okay, we'll forget the -1 to the signature of pi. Okay, so if you take a very simple example, so let's say 1, 2, 0, no, let's put 0, 1, 1, -1, 1. Okay, 1. Okay, I have a 3 by 3 matrix. What is the permanent? Okay, so I develop along the first line. There will be 1 times the permanent of this one, which is 2 plus 1, 3. So it will be equal to 3 plus 1. And then you remove, and there will be 1, 0. Okay, so it will be the permanent will be 3. So I develop along the first line. So I have 1 times the permanent of this smaller matrix. And this is 2 minus 1, so 2 plus 1, 3. And then if I develop along...
1 by minus, it's like you're computing determinant, not permanent. Minus 1. It should be 2 minus 1, simply, I guess.
Do you do a... Yeah, could be. I don't think so. Because you... yes, of course, you're right. 2. So 2, so it would be 1. Yeah, of course, my mistake. Okay. 2 plus 1. 2 minus 1, 1. And then if I develop along this factor, I guess 1 plus 1. So, okay. 2. So it's still 3. Okay, very good. So it means that when you add 2 mistakes, sometimes you can have a right result, right? It's just luck. Okay, but think about this. Sometimes luck can help. Okay, you'll see this in a minute. Okay, so now what's classical about the determinant is that, and this was actually observed a long time ago, is that, you know, it's much harder to compute than the permanent is much harder to compute than the determinant. Okay, and typically, what's very hard is I give you A, and suppose I give you a numerical value, alpha, say 17. I ask you, okay, now verify that this is correct, that alpha is a permanent of I. Okay? Now, is it something that you can do in this framework with a small certificate? And now you have a verification problem. Okay, you have to verify that the couple A alpha is correct. Well, nobody knows how to do it, and nobody believes that you can do it either. And I will show you some way to do it in a minute using approximation. Okay? Now, this is the typical problem which is called sharp P. So for those of you that know what sharp P is, and when you ask a decision problem using a problem sharp P, then you introduce this class P to the sharp P. Because you're making a polynomial computation using an oracle with your sharp P. And this class is essentially in between the polynomial hierarchy and P space. Okay? So it will be my second problem. And my third problem will be extremely classical and will be SAT. Okay, so I'm sure that if you've been to a computer science class, you all know what SAT is. With also the version called QBF for quantified Boolean formula. Okay, but SAT typically what you're given are Boolean clauses. Okay, and you want to know if they are satisfied. So, for example, you're given P1 or P2 bar and P3 or P2 bar and P1 bar, for example. Okay. So here you have 3 formulas, and then the question is the end of the 3 formulas satisfied? In other words, is there a way to assign 0, 1 to P1, P2, P3 so that I satisfy the 3? Okay? So this is a typical SAT problem, and you can see that it is, of course, the NP problem, because if I want to convince you that it is satisfiable, then I will send you the assignment. Okay, so for example here, I'm pretty sure that I can find an assignment. So P1 will be, so P1 has to be 0 by the third clause. Okay, and if P1 is 0, then P2 is also 0. Otherwise I don't satisfy the first. And if P2 is 0, then P2 bar is satisfied, so P3 can be anything. Correct? So for example, 0, 0, 0 is a satisfiable assignment. Okay, if you give me this, all I do is that I evaluate each formula, satisfy it's true. Okay, fine. Now I could now do exactly the same thing as I did with graph isomorphism, is reverse the question. Okay? In other words, I ask, is it, instead of asking, is it satisfiable? I say, show me that it's not satisfiable. Okay? Is it not satisfiable? Well, in which case, you are pretty much reduced to enumerate all possible valuations and then to check that each of them miss some of the formulas. Okay? So you are also in this situation. Now, if you're on the QBF version, is that you start asking question where you quantify, so for example, you want, is there a value on P1 such that for all value on P2, there exists a value on P3 such that these formulas are true? then of course it's kind of harder to figure out because you have to figure out, I'm sure on this simple example I can figure out, but okay, so usually people call this will be C1, it will be C2, it will be C3, so you want to satisfy this. And of course it's much harder problem, and this problem is in the class P space, which is here. Okay, so with a small introduction, we have three very classical problems, and you can guess that some of them are clearly in NP. Whether they are in co-NP is not obvious, and some of them are actually, more complex than NP, because if I give you a value for the permanent, to tell me if it's true or if it's false, it doesn't seem to be much simpler. Okay, and it's pretty much relies on computing the permanent. Okay, so this is a typical example that people think of. So now let's move to the second topic, is what is an approximate proof? Okay, so if you so now I'm going to tolerate some error. Okay, so it's very important to understand where do you put the error and how and so on and so forth. Okay, and there will be three models. The first model is called an interactive proof. Which we are going to introduce in a minute, is that we're going to change two things. We're going to make V probabilistic. It will take some random flips. So R is a random coins. It means that R is 0, 1 with probability 1/2. Okay, this is this notation here. Okay, the random uniform. So it means that you have a value with probability 1/2. And then we'll have an interaction. In other words, the verifier will allow to ask the prover some questions. Okay? And we're going to see an example of this in a minute. So interactive proof, there are two ingredients. First, of course, interaction. It's not a one-way thing anymore. And second is randomness. Random coins, and the model we take is a random coins are private. There is also a model where the random coins are public, it's slightly different. Okay. Now, the fact that you have random coins here means that the verifier will convince himself that the prover knows the answer with high probability. Again, the fact that you have these random coins, we're going to flip many coins, so you have this probabilistic space, which is very simple, of sequences of 0 and 1s, okay, of length k. Each sequence has a probability 1/2 to the k, okay, and this is our probabilistic space. And now, when I want, high probabilities, I mean that the error is as small as you want. Let's say, the epsilon error could be, say, 10 to the minus 10, typically. Okay, so if you're running a computer, an algorithm where the rate of error is this, usually people, especially if you come from physics, you should be alarmed that usually the components that compute, they have a rate of error which is much bigger than this. Right? So if there is an error, it's probably more likely due to a component than to your algorithm. Okay, so in other words, for all practitioners, this means truth. Okay? And pretty much everything we do is the same, right? Every time we do random verifications, when I mean high probability, means the error is anything you want. You want 10 to the minus 20, you can get 10 to the minus 20, it doesn't change anything. You want 10 to the minus 100, you get it. Okay, nothing changes. All right, so this is, of course, the mystery of this approach. Okay, Now we'll see, okay, so here the problem, as you'll see in a minute, is interaction. Okay, and it's very much like, I'm sure that you've been to some oral examination where you have a teacher asking you questions, right? And his next question is usually dependent of what the answers you have done before, right? Well, it's exactly like this, okay? Here I'm going to ask questions, be careful. My next question depends on what you answered before, okay? And this is how I'm going to collect extreme power to verify things very efficiently. Okay, so some people, of course, say, well, okay, this model is extremely tricky and the interaction does the whole thing, which is, of course, true in some sense. So maybe they want to remove the interaction. Say, okay, let's go back to a standard proof. Okay, remove the interaction. And this is called a PCP. Okay, so probabilistically checkable proof. Probabilistically checkable proof. Okay. But then what you have to eventually think about is very long proofs. Okay, so here the model is a little bit different. So you have to think of an extremely long proof, potentially very long proof, exponential. So maybe you have a proof which is of length exponential. Okay, but then the verifier will do the following thing. He will look at position on the proof and look at the bit which is written here. So this is the word, you know, whatever is written here in the interaction, you can think of a binary word. Okay, so the certificate or the proof, think of it as a binary word. So it's an element, say, of 0, 1 to some m, and it could be that m is exponential. Okay, so now I take a position I, and I get, so if you call this pi, I get pi of I in one step. Okay, so I can read, I figure out the position, I read pi of I. I use randomness, and by checking some position, I want to convince myself that this proof is correct with high probabilities. So I remove the interaction, but for the moment I tolerate exponential long proofs. Eventually we'll see that you can think also of polynomial size proof, but it's somehow harder. But then the key thing now is I only want to read finitely many positions here. Okay, so the question I ask indirectly is, can I read finitely many positions of a huge thing and convince myself that this is correct with high probability? I don't read the proof. Okay, so second model. So we'll see that it's entirely possible.
And verification is also in polynomial terms.
Verification is in polynomial terms. Okay? All right. And then the third situation, which is of course much more practical, as I'll mention a few applications, is an area where we push the approximation one step further. And these times we say the following thing intuitively. Well, instead of sampling the proof, why don't I sample the data? Okay, think of this. Like, what do I mean by sampling the data? If you have a matrix, I can sample the values of the matrix. If you have a word, I can sample the position, the label of the word. If I have a graph, I can sample subgraphs. Okay, now we'll see this in a minute. And then, say here, you know, the framework is slightly, here you have to think of a property of the object, so property of graphs. Think of a property, okay? So the property is, are the graphs isomorphic? Are these formulas satisfiable? That's a property. And now, I'm asking, okay, I don't want to read the data. Okay? So in other words, think of this thing. So you're trying to import the idea that you get from PCP. Okay? So if you have a huge certificate, you actually don't need to read it. Okay? If you sample it, it can be enough sometimes. Okay? Now, if you have data and you sample the data, okay, is it enough to decide a property? Well, for many properties, of course, it's certainly not enough. But now you want to introduce another parameter, which is a distance. Okay, so now we're going to have an extra parameter, which is epsilon. So epsilon will be now a distance on the object. On the object. Okay, so I have to think of. No. Okay, so think of, let's take graph, for example. Okay, so you have a graph. Okay, I imagine, so you have edges, whatever. And now you do the following thing. Is that you think you're going to use what is called the edit distance on graphs. So what is the edit distance on graphs? Well, you tolerate that you can suppress an edge, add an edge, add a new point. Okay, so every time you make an edit operation, is adding an edge, removing an edge, adding a node, removing a node. That's what an edit operation is. Okay, and now you introduce what is the distance between two graphs. Okay, well, the distance between two graphs is going to be the minimum number of operations. So when I start in G1, I end up in G2. And of course, it would be symmetric. If I started in G2, I would end up in G1. Okay?
Do you mean you want to end up in G2 or in some graph which is isomorphic to G2? Or just in...
Okay, very good question. Usually, when people use the edit distance, they assume that they work on the same domain. Okay, the domain is the same.
Yes,
okay.
But if you represent graphs as matrices, do you want to start from the adjacent symmetrics of G1 and end exactly in the adjacent symmetrics of G2?
Yes.
Not
yes.
the isomorphic.
No, but the question is very pertinent because in some models, indeed, you don't assume that they have the same domain, and in that case, you work modulo the isomorphism. Okay, and so graph isomorphism is going to sneak into the distance, and then you get trickier situations. Okay. Now, if you have a property, so a property is essentially a subset of graphs which satisfy the property. So what is the distance between a graph and a property P? Well, by definition, I should write it somewhere so I can keep it. Because it's a sort of a general thing. What is it? So let's think of the property P. Like, well, I wrote it with a double P. Okay. Okay. So maybe you've seen this because it's kind of a classical situation. So it's going to be the mean over G prime in P of the distance between G and G prime. Okay? All right. Okay. So what is the maximum value of the, so this is what is called the absolute distance between two graphs. And of course you can think of distances as a relative measure because it's easier to stick the distance between 0 and 1. So you divide by the maximum distance. So in the model I take, okay, so the relative distance, let's call it at least bar, is actually, you know, you divide by n squared. Okay, because the between two graphs, I mean, the first graph is a complete graph and the empty graph. Okay, in which case you have to add all edges, so you have n squared edit, and this is actually the optimal. So if you relativize by n squared, you end up with a value between 0 and 1. Okay, and now you're going to say that you are epsilon far from the property. So definition. G is epsilon far from P if the relative distance is bigger than epsilon. Okay? All right. So now what are we going to do with the property testing? Now we're going to relax the verifier to a new model, which is going to be maybe this picture. So the picture will be, okay, so the verifier, well, here, don't think of a prover here, think of the data. So here the finite structure. So let's put the data. Okay? The prover does nothing. Okay, so but the verifier accesses the data with random bits. Okay, you maintain a random bits. So if I have a graph with n nodes, okay, I hope everything see that essentially by flipping log n bits, I can access every node. Okay, because you know you have 2 to the log n is precisely n, so you access every node uniformly. Okay, and then maybe you want to. So here on graphs there are 2 models. If you are on dense graph. Okay, let's suppose we're on dense graph for simplicity. So you access 3 nodes of the graph. Let's call them x1, well, x2, so k nodes. Okay, and then you build the subgraph of G based on these k nodes. So anyway, you connect these k nodes by the edges of E that you see. Okay? This is called the induced subgraph. Okay, which is called, now this is a G, and this is a random object, which is GK. Okay? All right. So now, property testing, what is going to be? It's going to be that you have to have a verifier that decides between G is in the property and G is epsilon far from the property. From P. Okay? When G is epsilon close, you don't require, I mean, you don't guarantee anything. In other words, okay, a tester, an epsilon tester, is going to be a randomized algorithm such that if G is in P, it will say yes. And if G is epsilon far from P, it will say no with high probability. Okay? And that opens to a very practical area, which is the area of, so I make one word on application because I know that some of you may think that this is extremely theoretical. So now I want to convince you that it can be very practical. Okay? And if you like this area of computer science called big data, Okay, then you're going to see what happens. Because big data means you can't read the data. Okay, it would take too long. All right, so here I have a model where I sample the data. From the samples, I answer you approximately in this sense. Okay, so I'm going to convince you of the following thing, and this time I'm going to take much I'm not going to take graph as my basic model of data, but I'm going to take words and trees. Because it's going to be easier, and it's easier to understand also. So on words, there is a notion of an edit distance. Okay? So for example, if I have the words A, B, A, editing means I can remove a letter. Okay? So now I have A, B, A. I can modify, for example, this A into a B. So I modify A, B, B. And now maybe I add another letter, say A. Okay, so I make 3 edit operations. Okay? And you can think of now 2 words are epsilon close if their number of edit operations divided by n. Now the n will be the main factor because now the distance the maximum distance is n. So now everything is divided by n and not by n squared. And 2 words are close if their edit distance is smaller than epsilon, therefore, and so on and so forth. And then, so the typical thing that people do is they take regular expressions. So for example, let's imagine you have A, B star, A star, B star. Okay, so everybody understand these notations, right? Because it's a basic object that people treat in computer science. Okay, so imagine you have a word of size 1 billion, which is not uncommon if you're talking about biologists that study DNA, for example, but if you're talking about people storing Twitter messages, that's the type of data they have. And now you want to say, okay, whatever you have, is it close to this regular expression or is it far? Okay, and I want to show you that I can answer this. I don't have to read the word. I only sample the word. From the samples, I will answer this correctly with error probability 10 to the minus 10. But of course, there is an epsilon. And if you want epsilon going to 0, my number of samples will go as a function of 1 over epsilon. You have more samples, but nevertheless, it will be finite. Okay? And now let me show you the big application of this thing, which is, I think, very current. If you're interested in big data like Twitter, I discovered that it's very popular in Russia. So what happens in Twitter is that you have databases that are called NoSQL databases where you have many servers, about 10,000 servers. Okay, and think of the servers. Let's suppose I have 3 servers, and each one store a big word. Here I store W1, here I store W2, W3. Okay, each one is big, like 1 billion characters. All right, and now, so I don't have 3 servers, but I have 10,000. All right. Now the game is the following. So this is a very practical game. So if you do this efficiently, this you can make the difference at the moment. Okay, so now the game is the following. You can think of, okay, from each server you could build some statistics. Which statistics? That's a question. But I want some statistical information about the servers, okay, so that I can play the following game. My game is this. I announce in which way I'm going to combine my sources. For example, I could combine W2 followed by W3 reverse. Reverse is like this, okay? So that's my first instance. Okay? And what I want to do is get the statistics from W2, get the statistics from W3, combine them, and answer this question in this sense. Okay? Now, after that, I have another query, W10, followed by W8, followed by W1 reverse, followed by W1, if you want. You combine the statistics of my sources, and you answer correctly. Okay? You never read the data. All right? And I'm going to show you that this is entirely possible, but you have to think about which statistic you get. So only very specific statistics will answer this, not any statistics. Okay? And at that point, we touch a very practical area, which is the area where we never read data. No, data, you never read it. You know data by statistics. Okay? Maybe the statistics are rich enough so that you can figure out what you want to figure out. Maybe they are not rich enough, in which case, give me better statistics. Okay? So this is where this area goes to a very practical thing. Okay? So if you're still here on Sunday, I will give you the statistical information you need. And I will show you that if you get simpler statistics than the one I will define, you don't get this correctly. Okay, because of course you want to do it for any regular expressions. Okay, so just imagine you have hundreds of different regular expressions, and you want to essentially classify your data. Okay, I announce a new combination of my data, and just tell me which of the regular expressions is it closer to. Okay, it's kind of a mixed. And if you do this, now you have a market with Twitter. What Twitter does is that, of course, it stores trees. Okay, and it stores trees in a JSON format, which is some kind of variation of XML, but already there is some variation. And the depth of the trees is very small. Okay, so if you have trees that are very shallow and not so deep, they behave like words. So the first approximation, if you understand everything for the words, then you can do it for the trees too. Okay? So this is
Can I answer one question?
Yeah.
Do you sample not only letters but compute some statistics?
I will. Okay. I will sample the words, but
Letters from it.
okay.
And then aggregate.
Okay. So when I say up to now, when I say sample, I get a position, and from I need a subwords of length k from that position. Okay. So in other words, I'll make a first variation is that not only I want one letter, but I want the word of size k from starting at that position. Okay? Imagine, so k will be typically 1 over epsilon. How many samples? I need about 1 over epsilon square. Okay, but these numbers don't depend on n. Okay, this is going to be very crucial. Is that there's something I didn't say about on the tester. To be really interesting, people want the tester's complexity to be independent of n, only on epsilon. Okay, so whether you have 1 billion to 100 million, it doesn't make a difference. Okay, and of course it is totally counterintuitive if you're a computer scientist, where every bit counts. Here you're saying no, bits don't count, statistics count. Okay, it's kind of it's kind of an interesting twist, but not any statistics. So that's the point I want to make across. Okay, I'll give you the right statistics if you're still here on Sunday. But by the way, there is a website, and on the website, sort of classical, say, chapters on the first 2 models, actually on 3 models, and then there's more advanced slides on this story with notes that are actually the current research at the moment. Okay, so you can follow this and you have the details. Okay, but here's what I want to insist. I want to insist on 3 different models where in each case we verify, but we verify in a very different way from the approximation point of view. Okay, here I have randomness and interaction. Here I have only randomness on a large proof and I sample the proof. Here I sample the data, but I have an epsilon, which is of course dependent on the distance on the object. Okay, and that makes of course a tremendous difference. And the last one is the practical one. Okay, the 2 first are theoretical ones, but the 2 first gives you ideas that are recycled here somehow. You know, that's how you have to figure out. Okay, so now let's start with the first model. And so maybe some of you have seen this already, but you know, it's still something very useful. So let's see how to erase the complexity picture. I want to leave this. Okay, maybe I erase this for the moment. Okay, so let's do interactive proofs. And now, how do you define interactive proofs? Okay, so we go back to the prover and the verifier, and then you have some data. So the data, typically, I call it X. Okay, so in case of graph isomorphism, X is you know, the pair G1, G2. And you suppose you give them with the adjacency matrix, for example. That's good enough. And now, so first of all, how many of you know the protocol for graph non-isomorphism? You do, okay. All right, so I'm sorry to, but it's kind of a, you know, it's a nice, the advantage is very simple, and you'll see the beauty of it. And then after that, we'll go to a more advanced protocol for the permanent. It's slightly more involved. So, okay, so that's what I expect to do today. Tomorrow morning, tomorrow, first part of the class, I'll do the PCP using SAT as a basic driving example. And in the afternoon, we'll start the property testing. And I'll use slides because I need to go faster. So, you know, there will be an acceleration somehow. So, but if you don't follow, you have all the details. And then on Sunday, we'll finish on the practical property testing. And non-deterministic property testing is something I will mention also. And then we'll concentrate on applications. Okay, so let's get now to the first model. Okay, so what you want is you think of the prover. Well, okay, the verifier is going to start the game, the interaction. Okay, he's going to ask questions. Okay, and the prover will give answers. But then you have to formalize this as functions. Okay, so essentially you think of the verifier first question as a function, say, of rho and of x, and it's going to define a v1. Now v1 is a word, you know. Okay, and then the prover will have to answer to v1, so he knows x, he knows v1, and he provides a u1. Not a u1, that's p1. Well, p is not very good. Well, that's a u1. Okay. All right, and then so that's the first round. The second round, of course, will iterate. So v2 will take some rho x, u1, and produce a v2, and then p2 will take the rho, the x, not the rho. You know, here it's very important. The prover doesn't know the rho in this model. Okay. So the prover doesn't know the role. Okay, only the verifier knows the role. So the prover knows the data, of course. He knows the first question was U1, no, V1. And second question was V2, and he produced U2. Okay? And then iterate this for k steps, if you want. Okay? So Vk, well, usually people go to k minus 1. So it will take the U1, Uk minus 2, and he produces Vk minus 1. And then the Pk minus 1 will take, okay, here the x, and then the V1, Vk minus 1, and he produces a Uk minus 1. And then at the last step, the verifier will say I accept or I reject. So therefore, Vk of everything has to be 0, 1. Okay, so I interpret as V, if it's 1, he accepts, and if it's 0, he rejects. Okay, and the notation typically that people take is to say that PV of x equal 1, if and only if Vk of everything is 1, and otherwise it's 0. Okay, so that's a notation. And that's a protocol that iterates k times. Okay, all right, so now what do you want? So you imagine now you have a language. So our language is going to be in a minute graph. So the question is, I want to say that the two graphs are not isomorphic. So I imagine that the language is a set of pairs of G1, G2, such that G1 is not isomorphic to G2. Okay? And now I have to define when does a language has an interactive proof. Okay, so L has an interactive proof. So if there are okay, so I would say there is a polynomial time verifier. Okay, so a verifier is defined by the function v1, v2, vk, such that, okay, so here you have to be, here is a trick in the definition. Okay, so if there are two conditions, right? If x is in L or if x is not in L. So if x in L, you want there exists a prover such that PV x equal 1 all the time, and to make the point, you can write it like this: probability that PV x equal 1 is 1. Okay, so probability on the random choices that the verifier has made. Okay, so in other words, if you have this definition, the verifier should always accept. Okay, with probability 1, if you want. No. Sometimes, if you look at variation of IP, you know, some people don't put 1 here; they put 2/3 maybe or something. But that doesn't make a difference. Okay, and if x is not in L, okay, so this is where the historic definition was hard to catch. And then it's for all prover p prime. Okay, for all prover p prime. So the probability that p prime v x equals 1 Okay, that should be small, because you don't want if the input is not in your language, the verifier should reject. So no prover should force him to accept with probability more than 1/2. Okay, so that's, okay, this definition, it goes back to the 80s, 1980s, so it's not that old. But it took a long time, maybe 85, 88. If you look at the literature in theoretical computer science between, say, mid-70s to late 80s, there were about a dozen attempts to have the right definition of randomized NP. Okay, so what you're trying to do here is to say, okay, you have this, when you compute with randomness, usually you introduce these complexity classes BPP, and okay, so usually BPP would be, this is actually not let's write it like this. That would be BPP like this. And the question for a long time was, what is the equivalent of BPP for NP? Right? So it took a long time until people centered to this definition, and this definition is actually right for many reasons that I will explain for a minute. So just here point to the asymmetry of the, here you want probability 1, here probability small, okay, less than 1/2, okay? All right, so maybe it doesn't ring too many bells to you, but let's see, until you see the first example, then you'll understand. So let's take this graph of non-isomorphism. And then everything becomes clear. Okay, so X is 2 graphs. Entrance is 2 graphs. Okay, I'm the verifier. What do I do? Okay, so first thing, I flip a coin. So my row, I'm going to change slightly my row. I take 1 or 2 with probability 1/2. Okay, so I take a random row, and then I look at, say, G sub row. So it's either G1 or G2, okay, with probability 1/2. All right, and I'm going to make an isomorphic copy of G row. So then I generate a random pi, and I will define H, which is pi of G row. Everybody understand what I'm doing? Okay, so you have 2 uses of the randomness here. First of all, the main use of the randomness is picking one of these graphs. Okay, you don't know, of course, the prover which one you pick. And you're going to send it to him and ask him, well, is it isomorphic to G1 or isomorphic to G2? So you have to think of the prover. In this definition, there is no constraint on the prover. Now, one constraint on the verifier, okay, the verifier is polynomial time. I wrote this, but the prover, there is no constraint on the prover. The prover can be anything, okay? All right, so if there is no constraint on the prover, if you ask him, given H, is it isomorphic to G1 or to G2? He should tell you, because potentially he knows everything. Okay. Now remember, you, the verifier, you don't know. You're too weak to figure out if 2 graphs are not isomorphic or not. You don't have the power to do this. But somebody claims he can do it. Okay. Well, let's check him out. I build this G row, either G1 or G2. Then I make an isomorphic copy of it. Okay, so I have a second use of the randomness to get this isomorphic to this random pi. Okay, so if you remember, pi is a sequence of words in one n. Essentially, I take the first one randomly, and then I remove it in my list. I take the second one in the remaining of the list, and so on and so forth. So taking a random pi is something easy. Okay, I don't detail it. So therefore, I can build that very easily. And now, the protocol is exactly this. So H is what I give to P. Okay, so H is my V1, if you want. okay? And I ask the prover to send me one bit, okay? Is H a copy, an isomorphic copy of G1 or of G2? So he's going to send me, so is V1 is 0, 1, or let's say 1 or 2. If it's 1, I interpret that he thinks that rho is equal to 1. And if he sends 2, I interpret that rho equals 2. Okay? So of course, if it's not true, I don't believe him. That's a way for me to catch him, right? That's the key. Okay, so let's analyze exactly what's going on here. It's not entirely trivial, because of course there are two cases. So the case one is when the two graphs indeed are not isomorphic. Okay, so case one. G1 is not isomorphic to G2. And things go easy. Okay? Things go easy in the following sense. So, when he sees H is isomorphic to one of them, but not to both, because they're not isomorphic. Okay? So therefore, there is no doubt. If he knows, he should not make any error. Okay? So in other words, if he makes an error, I reject. Okay? So here in the protocol, I should have added that if rho is equal to 1. Okay, so in other words, I compare. So here, what I should have said is if rho equals V1, accept, and otherwise reject. So rho V1 you accept, and rho different from V1 you reject. Okay. Which is my PV x equal 1 or PV x equals 0. Okay? So this is my decision. All right, so let's go back to I send him this. There is only one correct answer. Okay? So therefore, if he answers correctly, I accept. And indeed, there is a prover. Imagine a prover that knows exactly. He should make an error, you know. And therefore, I will have this. In other words, there exists a prover such that he doesn't make any error. I don't make any error in this test. Okay? So therefore, here you validate the fact that PV x equal 1 with probability 1. You see this? There exists a prover. Usually it's called a honest prover, okay, which doesn't try to lie to me, okay, and I catch him in a fair way, okay. So therefore, this is correct. Right. What is correct is probability that this is true is 1. Now, of course, the other situation is more tricky. Suppose G1 is isomorphic to G2. Okay, well, I'm going to get this G of rho, this H, but H is isomorphic to both. So it's isomorphic to G1, it's isomorphic to G2. So when I'm asking the prover, tell me which graphs are different, he has no way of knowing. He can't answer this. He has no information to provide the right answer, and therefore he will answer at best in a random way, and therefore he will make 1/2 probability of error. Okay, so therefore here the second situation. So here you can. I'm sketching a little bit here, but what it means is that the probability that any prover convince me that the graph are non-isomorphic is precisely 1/2. Or less than 1/2. Okay, maybe less than 1/2 is a better way to put it, which is exactly what I want. Okay, so here the the beauty of this protocol is that it's very simple. Okay? It's very simple. The verifier doesn't know how to solve the graph isomorphism. Okay? But the prover claims he can. Okay? So I want to verify efficiently. And you notice that I need to interact at least twice. Okay? I ask him a question, he gives me an answer. Okay? Now, of course, if I want to amplify the error probability, I will ask him many times, and this will go to 1/2 to the k. So if you want 1/2 to the k to be 10 minus to the minus 10, then you figure out that you probably need 20 trials. Okay? But you can see that the protocol is extremely simple. Protocol is extremely simple. It guesses one random bit. You use some random bits to generate a random permutation, but this is less important. Okay? Makes a random copy, sends a random copy, so it does send n squared bits here in one way, and the other way it receives 1 bit. Okay? And then it maintains this condition. Okay? All right. So we make a break at in what, 15 minutes? We started at 6 about, no? So we can go for another 15 minutes.
May I interrupt?
Sure.
To understand clearly, in this protocol, the prover wants to prove that he claims that he knows how to solve the isomorphic problem.
Yes.
This probably a big difference with the situation when the prover says, I know that these two particular graphs are non-isomorphic. For example, the prover says, I know this is G1, this is G2, I know they're not non-isomorphic, they're too big to verify, to claim, to check this himself.
Yes.
Is there a proof for this case? Because this doesn't work because the prover doesn't claim that he can check isomorphism of any two graphs. So you can't give him this H.
Yes.
Because he only knows that G1 and G2 are not isomorphic.
Who knows? The prover or the verifier?
The prover knows just that he claims.
He claims.
He knows that G1 and G2
Yes.
are not isomorphic.
But he has to convince the verifier that this is correct.
Yes.
Okay?
Yes. Is there a proof for this situation?
There is the interactive proof here is a non-classical proof in the following ways: is that the verifier needs to interact, and the verifier needs to use a random bit, and he can only convince himself with high probability in this other case. But in the case you mentioned, there is no error. Okay, so if the two graphs are not isomorphic, which is the case you do mention, okay, the verifier will make a decision with absolutely no error. In this sense, in the sense that if a prover claims that he knows how to solve the non-isomorphism problem, he should answer the H question, in other words, return the V1 value correct. Otherwise, he doesn't. Okay, and that's what I'm checking. I don't know if I answer your question, but in the case that the two graphs are not isomorphic, okay, the verifier convinces himself with absolutely no error, in the sense that if there exists a prover that knows, he will get out of the test with probability 1.
No, probably you misunderstood what I said.
Okay.
In the problem you considered, prover says, I know how to solve isomorphism or non-isomorphism problem. And I can convince that I can solve this problem. In my situation, the first I say for 10 years I compare the graphs G1 and G2, and now I know that these two graphs are non-isomorphic.
Yes.
Can he convince verify this particular two graphs? He cannot do this for any pair.
Ah, okay. Here you're trying to build a classical proof of the prover that wants to convince the verifier of something. So you're trying to define a certificate based on this 10 years experience of computations.
Probabilistic, maybe some probabilistic, not exact certificate.
Okay. So you're trying something else. You're trying to define a certificate such that the verifier will accept with high probabilities.
Yeah.
But what's the probabilistic space? See, where is the probabilistic space? High probability, you have to have a probabilistic space behind. And this is where it is not clear, because if you build this certificate, you also have to build the probabilistic space on which the certificate is defined. If you claim high probabilities, or maybe you want to claim something else, you want to put the error in a different way. Okay, think of maybe user property testing. User property testing, I think that it's more like what you have in mind. What you have in mind is, I certify that this graph is close to be isomorphic, in the sense that I can remove a few edges or maybe, fiddle around and they will be isomorphic. So in this case, the certificate is what did you remove, what did you add in each one, and where is the pi? Here you go back to now, give me the permutation. If you tell me, look, I removed these edges, I added this one, this, and now is the pi, then it's entirely okay. Okay? But you say, I think that's what you have in mind. There is no probability here, there is an error distance in this sense. Okay? But you could entirely maybe edit with the probabilistic space. I flip a coin. If it's a head, I remove this edge. If it's a face, I remove that one. Okay? Aha. So this becomes more interesting here. Okay? And then we're mixing the two. Okay? But everything is possible.
Yeah.
Everything is possible. I think what you have in mind is more something like this, which really shows that this concept of approximate verification, there is space for mixing them. Okay, and actually, so approximate isomorphism is something that exists. Okay, if you look at Google, put epsilon isomorphism, and then you'll see people that have worked on that recently, very recently. Okay, but here we settle for a model defined exactly like this. Okay, and for that model, the simplest protocol is this one. Okay, and I hope I convince you that once you've seen this and you realize, here there are two things that are very important: to interact and flip a coin. And actually, what is important is that this coin here is private. It's not obvious to see how you would flip a coin public, so that P sees the flipping. If P sees the flipping of the coin, then the protocol should be more difficult, and it is. Okay? So these are alternate models that are called Arthur-Merlin games. So AM means Arthur and Merlin. So for those of you that heard this. Okay?
And is there a model when prover is a bit less smart?
Okay. If you can, so people have asked this at the beginning, and essentially you can restrict the prover to be p-space. Okay. Okay. And why do you can restrict the prover to be p-space? Because the one of the fundamental theorem here is that the class of languages that have an interactive proof is precisely p-space. So usually people call it IP. IP is not the internet protocol. but interactive proof, and it's a complexity class. It's a class of languages that have an interactive proof in this sense. Okay, and it is p-space. So because it's p-space, you can restrict the prover to be p-space. If you restrict the prover to be, say, NP to the co-NP, or in the polynomial hierarchy, then you get interesting twists too. There are several interesting stories going on if you restrict the prover to be not p-space, but somehow around here. That exists too. Okay. The advantage of this protocol is that it's very simple. I think you can get the idea. It's only a theoretical idea, but it's an idea that you'll see in different contexts. Okay, so my plan was to move to a more sophisticated protocol for the permanent, because that gives you, I mean, on the way we see many interesting things, and I think that's probably what we should do now, because if we can do the permanent for the next hour. So maybe for some of you that don't like the technicalities, that may be a bit boring, but I will somehow simplify the subtleties, and then so this time we can start the PCP, classical PCP tomorrow on the first part, and then start the property testing on the second part, and then so that will be in a good position. Now PCP, I want to do what I call the easy PCP. Okay, the easy PCP is when you allow the proof to be exponentially long. The hard PCP, when the proof is polynomially long. No, you need 10 hours to explain this, and pedagogically it's not so clear that you get the idea. Now, property testing is clearly the most practical notion, and the notion that is, where the current research goes and extremely active. And if some of you, for example, Twitter is an excellent basis for doing this. You observe tweets, you have all these servers. So the advantage of Twitter is that the data is public. Okay, so what is typically what people do is that they get some hashtags, and they get a continuous flux of tweets. Or maybe you've done this, or it's a typical thing that we ask now in computer science classes. And okay, so getting a flux at a given time is essentially free. In other words, you can have 100 flux with different hashtags, and that's free. However, if you ask for the tweet yesterday or months ago on certain hashtags, it gives it, you will get some answer, but it will block you for 15 minutes because, of course, you have his databases working, so it doesn't want you to start, ask. I mean, it costs him money to give you this answer, so this is it's not free anymore in a sense. Okay, and so that gives very interesting examples of what we can do using the randomization on the data. I explained that to you, and you'll see that there are practical application to that in many areas. And I'm sure that if Twitter is is commonly used in Russia, you can do pretty much the same thing. Still a relatively simple protocol, very pedagogical. And then on the way we see something which is very useful, which is called Schwarz-Zippel. So maybe you know what Schwarz-Zippel is, but at some point, in all this area, there are a couple of key tools that you need to know. Okay, so chain of bound is one of them, and Schwarz-Zippel is another. Okay, you need about 5 or 6, not very many. And once you have these tools, then essentially it's assembly game. Okay, so remember now the language we have in mind is that we're given a matrix, and we're given a certain value, say A, and I want to verify that the permanent of A is A. Okay, so usually A is huge. Okay, to make to get a feeling of why the permanent would be huge, think of the matrix. So matrix is always n by n. Okay, now imagine that I put 2 everywhere. Okay,
matrix is always on integers. The matrix is always.
Yes, to make it simple, let's make it on integers. And actually, there is the area of the permanent even on 0-1 matrices. Yeah. Okay, which is But let's imagine that I have a matrix uniform with value 2. Okay, so you see, if you take a permutation, you get 2 by 2 n times. Okay, so you get 2 to the n. Okay, and how many permutation do you have? You have factorial n. So the permanent will be factorial n times 2 to the n. Okay? All right, which is huge, right? So we don't like huge numbers like this. So obviously we're going to make modulo some prime. Okay, because otherwise the situation gets out of hand. Especially because I don't have any special bound on the values, the integer values period. Okay, so what typically people take is a prime number p, which is between 2 to the n and 2 to the n squared. Let me check this because, oh no, between 2 to the factorial n, well, almost the same thing. No, that would be too big. It's actually between this and factorial n 2 to the n. Okay, but anyway, imagine a big prime number, and we're going to take all the values modulo that prime. Okay, so that values are never over the n bits. Okay, because otherwise, see, by the time you reach huge values, it could be that just to transmit that value takes exponential time. So I want to avoid this. Of course, there's a very small probability that I get confusion, because there will be 2 values that merge to the same, 2 huge values that merge to the same small value. But this will happen with totally small probability, so they will be okay. Okay? All right. So now, what is going? So you can, first of all, you can guess that permanent is a very, very tough thing. If I give you, imagine I give you a huge value here, people have no clue to verify if it's correct. But the obvious solution is to compute the permanent, okay, and to verify, compare it with A. Okay. This is, of course, different with a determinant, okay, because the determinant is totally related to the inverse of the matrix, okay? So you have to think of the same kind of problem with the determinant. You think of, for example, given A, I ask you to compute A minus 1, okay? Well, this has a certain complexity. But now the verification, so given A and B, I'm asking you, is B equal to A minus 1? Okay? So this is a computation problem, and this is a verification problem. Okay? But this is much easier than that. Okay? All you have to do is multiply A by B, and then look if you get the identity. Okay? So it's one of these cases where, although you are in the realm of polynomial time computability, verification is much easier than computation. Okay? Verification is one matrix multiplication. Getting the inverse, it's polynomial time computable, but some kind of an n cube, and then you have precision, some numerical values that can be actually very hard. I'm sure that if you are in physics, you know that you have huge matrices with totally crazy coefficients. Usually you get, you compute the inverse of the matrix and it's probably wrong, right? Because you have error that accumulates and the result is wrong. And you get two different machines, you get two different results. Okay? So actually, this area of verification is often used in that sense. Okay? And one typical application, actually historical application, is to, well, maybe I'll come back to the end, but to the area of computing with errors. Okay, so you assume, for example, you have arithmetical operations, but they make 30% of the time they make errors. Okay, question, can you reduce the error to 10 to the minus 10? Okay, answer yes, with techniques which are exactly like this. Okay, so in other words, when you deal with verification, often you prefer people that make errors. Okay? So actually computing with errors is much more fun than computing exactly. Okay? Because you'll see that you have errors everywhere, but somehow my verification will catch the bad guys very quickly. Okay? Even though everything is wrong. Alright. So, I'll give you an example for that at the end. Okay, so let's go back to the permanent. So now, what is the most natural thing to do when you have a permanent? Well, you're going to develop the permanent along the first line. Exactly like I did in the example, and you hope you don't make the mistakes I did with the minus. Okay, so in other words, you can always write A is a sum. Okay, you develop on the first line. So you're going to get A1I, and the permanent, what is called the minor, once you remove the first line and the ith column, okay, that will be the AI matrix. Okay? And you do it. Everybody see this? Now this AI is an n-1 by n-1 matrix. Right? You remove the first line and the ith column. Okay, it's called the minor. All right. So let's go back to this picture. And now the data is A. Big A, small a. This is a numerical value. This is a matrix, n by n. Okay? So obviously the verifier, it can do that, right? All right? So now it's going to ask the prover, well, okay, give me the values here. Okay, obviously now he says, okay, I can write this equation. Now, first question is give me the values that you see for a sub I, for each I. So you have n values. So then he assumes that the prover is going to provide these values. Let's call them AI. Okay, so this is what is called the extension phase. So extension phase is essentially, obviously, developing along one line. And then you get A1, AN. Yes. Okay, and then, then obviously I want to check that A is a sum of A1I, AI. Okay? Now this is provided by the prover. Prover sends this, and I check that this is coherent in that sense. Okay? If this equation is not satisfied, I reject. Immediately I reject. Okay? All right. But now you're reduced to n subproblems of size n-1. Okay? But of course, this is a problem, right? Because if we keep doing this, we're going to reduce to an exponential. At each time, we're going to branch by 2. by n or n minus 1. So, and then we have an exponential number of subproblems, and this is no good. Okay, so here is the magic that we're going to do. And the magic is I'm going to combine n questions into one question. Okay? Now, if there will be some error in one of the answers, it would propagate. Okay? And if it was correct, everything would go fine. The only thing I want is, and this is a reduction phase, is that I want to combine, see, the set of A sub I, okay, I have n of those, okay, into what? Which I will call B. Okay, and B will be of size, the same size as A sub I, so B of size n minus 1. Okay, so if I do at each stage a reduction by 1, then at n stage I will have a matrix which is of size 1. That time the permanent is the value of the coefficient, and I'm done. I could even stop at the matrix of size 2, but anyway, that's... So you'll see that we're going to interact this time n times, as opposed to the first example in graph non-isomorphism where we interact only once. Okay? Somehow it's feasible to prove that you need to interact n times. Okay? All right, so what is the magic here? How do we do the magic? So maybe you know. Okay, so this is... Sorry?
Multiply the matrices maybe by some different powers of 2, like we can then add some amount.
Something like this, okay? But there is a very standard technique. So the standard technique, I will write it here. It's called linearization. Okay, so you're going to think of, so linearization usually think of two solutions, for example, A1 and A2, you want to make one solution which is a mix of the two. Okay, so linearization in this case would be alpha A1 plus 1 minus alpha A2 with alpha some coefficients. Okay, that's what people call usually linear combination of two solutions. Okay? Now, if you have a linear combination of n solution, you could do pretty much the same thing. We're going to do this, but we're going to do something slightly more advanced, because it will simplify what we do after that. Is that we're going to build a polynomial by making some polynomial combination of the AI. Okay? So it'll be some polynomial, and essentially it will capture in one shot all the A1 A sub n. Okay? So what is this polynomial? So you have to think of, so B will be the sum of, so obviously AI some delta I of lambda I, and now what is delta I? So the variable of the polynomial is going to be lambda, and lambda, the delta I lambda is called interpolation polynomials, or sometimes the Lagrange polynomials, so they're extremely useful for many things. And it's essentially the polynomials which is going to be 1 when lambda is I and 0 otherwise. Okay? So it's going to be, so technically, what's the definition of lambda? Is the product of lambda minus j over I minus j, and then you do the product for I different from j. Okay. So maybe you've seen this polynomial. So what is, for example, delta 2? Lambda. Okay. Well, you see, so you do, it's going to be lambda 1 times lambda 3 minus 3 times lambda minus n divided by 2 minus 1 times 2 minus 3 times 2 minus n. You see this? So I put everything, but I remove the lambda minus 2 and I remove the I minus 2. Okay? All right, so what happens? If I put lambda equals 1, 3, 4 up to n, I get 0. And if I put lambda equal 2, then all this is going to be 2 minus 1, which simplify by this, and it's going to be 1. Okay, so delta 2 is 1, and on all other integers it's 0. That's why it's called interpolation polynomials. Okay, so you see what happens here, you have a polynomial in lambda. Now what is the degree of the polynomial? Well, it's going to be lambda to the n, right? So it's going to be n degree. N minus 1, thank you. In complexity, n or n minus 1, usually it's about the same. And so it's a polynomial of degree n, and if I check the value of the polynomial for lambda equals 1, I should get, it's like having the matrix A1, so on and so forth, okay? So obviously, what I'm interested in is what is the permanent of B. Now the permanent of B, it's also a polynomial. You see this? Okay, so I can erase now this. Now the permanent of B, okay? Why is it a polynomial? Because you imagine you have these n matrices, so you add, if you look at the coefficient here, the coefficient here is essentially the lambda 1, the delta 1 lambda, the coefficient of A1 plus etc. Okay, so here for each value you have a polynomial of degree n minus 1. Okay, each coefficient here. Right? So now, what is the degree of the permanent of this matrix? Sorry?
N to n times n minus 1, but it can be.
I think it's going to be n squared. Yeah, because you multiply lambda n by lambda n by lambda n, so it'll be lambda n squared. Right or not? I claim that the degree is lambda n squared.
N times n minus 1.
Yes, more. Okay, this. All right? Okay.
Minus 1 squared. AI equals size n minus 1 to n minus 1. Am I right?
Yes?
So it's n minus 1 squared.
N minus 1 squared.
Because AI is of I squared.
Okay.
But it can be 0.
Yeah, sure. Yes, okay. Let's go. Let's solve degree n squared. N minus 1 squared, but n minus 1 squared for purposes is n squared. Okay, so what am I going to do is now ask the prover to give me this polynomial. Okay, so this polynomial, you can write it as a sum of some coefficient p sub I, lambda sub I, for I going for between 1 and n squared, n minus 1 squared. Okay, so how many values do you have? Well, you have n squared values at the most, okay? Because remember, we're going to iterate this, so the first time you have n minus 1 square operation, but then after that we're going to reduce it to n minus 2 square and so on and so forth, okay? Because we're going to play this game many times. Everybody see this? My verifier, remember, we can ask anything, okay? So you give him n minus 1, n values for the AI, okay? He checks if it's coherent. Now it's reduced to n problem, n sub-problem of size n minus 1. He wants one problem, so the one problem is B, which depends on the lambda, okay? And now, when are we going to use randomness?
Choose lambda random.
Exactly. After that, we'll make lambda random on the domain that we're looking at. And then we hope, of course, that everything will go with high probability in the sense that if there is an error there will be an error on the B's. Again, that's what we have to show. So the error will cascade. So at the end, we check the error. Everybody see this? Okay, so the reduction step is a two-step process where we ask for this polynomial. Okay, so first you ask for, say, B is going to be the sum of, well, I shouldn't say B. No, B is a numerical value. So I want the polynomial which is the sum of the pi lambda I. And this is a permanent of the sum of the delta I lambda AI. Okay, so I build a linearization of my matrices with the interpolation polynomials. So this is my new matrix. Okay, I know it has a permanent of that type where the degree is smaller than n squared. Okay, so the verifier is going to give me all these coefficients. Okay, and now second step, I make R lambda random. So random on which field? Well, I suppose you can take random on this. Remember, we were modulo P for this big prime. So modulo 1P. I guess you can remove the 1. 0 is like 1. Okay. So random uniform. And then after that, it will define, that will define B will be exactly the permanent of this matrix when I replace lambda by R. So I should say maybe apply to R. And B, the small b, will be this polynomial you evaluate on R and will give you a small b. Knowing that we do everything modulo P. Okay? So in my reduction step, I'm back to one matrix, B, and one value, small b, of size n minus 1. Okay? Well, now I iterate. Extension step, this time I have n minus 1, subproblem of size n minus 2. I linearize them, and I do my random. Okay? So you see the magic here, the magic, the real, if there is something magic, is this operation. The first one is trivial. Okay? The second is how you reduce n problems, or eventually how you would reduce 2 problems in one. Such that if there is a mistake in one of the 2 values you gave me, there will be a mistake in the new value, and if there is no mistake, there will be no mistake in the new value. That's precisely what you want. You want the error to cascade. Okay? So that at the end, when you reach the matrix of size 1, and is that, this equation becomes only checking a value, and you accept or you reject if it's correct or not. Okay? All right, so now we have to show that the key, so we have to maintain these 2 property on this protocol. So you see this protocol is more advanced, there are more interactions, but nevertheless it's not the end of the world. The key idea is the linearization of many solutions into one. Okay? And that would be enough. So let's see, where do I write now? Wow, I can erase this. Okay, so I want to show now the 2 properties that are the key. So let's see, now okay, so the first lemma 1, I want to say that if we start with something wrong, so if A is false, then one of the AI is false. Okay, you have to think of a totally perverse prover who lies all the time, right? But you never catch him, right? He lies on the lie, and eventually everything goes fine. This is what politicians do. You lie all the time, and in the end, everything is, looks good, right? So this is a talent, of course. So just imagine that this is correct. This is wrong. Just imagine this is wrong. How could this be correct? Because if this is correct, if all of them are correct, then this equation has to be correct. Okay, so therefore this will be correct, but it is wrong. So one of them has to be incorrect. Right? So, in other words, if you start with a wrong statement at the beginning, in the sense that if I'm not in the language of the permanent, okay, then after each extension phase, I must have an error in one of the solutions. Okay? And then I want to say that if I have an error in one of the solutions, with high probability, I will have an error in B. Okay? Okay. All right, so that will be the lemma 2. All right, so maybe in the end I will erase this, but thank you. Okay, so this is of course a key to the protocol. Okay, so So if AI is true for all I, there exists a prover P, so this is a prover, such that V is true. Okay, so that's the first part. And second part, if for all P prime there exists an I such that AI is false, then the probability that BB is false is bigger than 1 minus n squared over P. So in other words, this is, think of it as epsilon, 1 minus epsilon. So it's big. Okay, so first part of the lemma 2 is of course addressing the case that this is true. Okay, so if it's true, there exists a prover which passes test. They give me the true values. Okay, and then because he gives me the true values, he also gives me the true values of the coefficient of the polynomial, and therefore when I'm going to do a consistency check, okay, I haven't mentioned the consistency check that I'm going to do here, but essentially checking that for lambda equal 1, I get A1, lambda equal 2 equal A2, everything would be fine. So therefore, if I take a random R, this will also be true. Okay, so here I forgot a slight check. Before reducing to BB, I should have said that I'm going to check that this polynomial is consistent with the AI in the following sense, that if I put lambda equals 1 in the polynomial, I should get A1. Okay, so in other words, the consistency check here, I forgot to mention it, but it's important. So if I put lambda, so the sum of the PI lambda I should have, I mean, this lambda is a power, okay? Yes, it should be like this. So this, if I evaluate it on, say, J, lambda equal J, I should get AJ for all J's. Okay? See what I mean? You give me a polynomial, okay? But why did I use this delta interpolation? I used this delta interpolation because when lambda equals 1, I focus on A1. When lambda equals 2, I focus on A2. Okay? And therefore, you better maintain this. Because if you don't maintain this, somehow you're lying to me. Okay? The polynomial, the coefficient you gave me are wrong. Okay? And if you lie to me, then I must catch you somewhere. So I have to catch you, and I want to catch you, of course, by taking the random lambda, by taking the random R. And this is the next, of course, condition here, is that for all P prime, so whatever prover, if at some point there exists a wrong statement, okay, then the probability that B is wrong is very high. Okay, and that's a key. Somehow the lemma 1 or the first part of the lemma 2, there's some easy statement. Second statement, most important, is that if you take this hypothesis that any prover, actually, you see what happens is that if you start with the wrong A at the beginning, we know that one of the AI is wrong, and therefore this hypothesis is true, and we want to conclude that the B is wrong with high probabilities. I mean, this pair is wrong with high probabilities. Okay? And you cannot get one here. That's the point. Okay? You cannot get the pair BB always wrong. That would be impossible with polynomials. To prove this, B, you need one of the basic tools of this area, which is called the Schwarzschild. So I put it here, because if you want to remember one thing about this protocol, just remember this. Okay, so here's the lemma. You consider a polynomial in n variable of degree d. So what is the degree of a polynomial with many variables? Well, you take the monomials and you add the degree of each of the variables. Okay? So for example, if you have a x1 to the 2 times x2 to the 5 times x3 to the 7, okay, the degree will be 14. Okay, so just imagine you have a polynomial of degree d. Now, of course, most of you are used to a polynomial with one variable of degree d, right? And what you learn in elementary algebra is how many roots can you find on a polynomial if you bound the number of variables and the degree and the domain. Okay, so we're going to imagine that all the xi are on the domain 0, 1 up to maximum value, which is called m. Okay, and of course I only consider that xi take integer values. Okay, so I have m plus 1 possible values. Okay, and I want to bound the number of roots, so the number of x1, xn, such that p equals 0. Okay, so some of you know the bound. What, or do you have any estimate?
We can put polynomial in these fields.
The polynomial, yes, polynomial. Yeah?
So I mean,
okay, the bound, like, it's actually exact. It's d to the m to the minus n minus 1. Okay, so think n equals 1. N equals 1, so therefore you have, this is 1, and therefore you have d roots. If you have a polynomial of degree 2, you have at most 2 roots, right? Okay? And if you have degree 17, you have 17 roots. Okay, but when you have many variables, it's not obvious to see where the, is it n to the m or m to the n, or, this is slightly tricky, but this is exactly the bound. But most people use it in the following way. They conclude that if you take, imagine you take random points, x1, xn, on the domain of, okay, to make it simple, I will go to m minus 1. So I want the size of the domain to be n. Okay? Okay, so question is, if I take, what is the probability from this? I mean, one of the corollaries is this, is that if you take random points, what is the probability that you get a root? Okay? So the probability that taking that's p of x equals 0, probability, if you take the x's random uniformly on this domain, okay, it is at most d of m. Okay, and that's easy to see because how many points do you have? You have m to the n. So you divide the number of roots divided by m to the n, and you get d to the m. Okay? But you see that this is essentially m is huge. M is going to be a prime number. So it's an exponential number. So therefore, the probability to hit the root of the polynomial is extremely small. Okay? It's 1 over m. Essentially d over n. Okay, so now in which sense are we going to apply this now? Okay, so what is the probability that indeed this will be true? Okay, well, it will be the probability that when we take r, so here I have a polynomial in one variable, okay, so back to n equal 1 here. Of course, this n has nothing to do with the n there, okay? So essentially, once we have so n variables, so you see, interestingly, this bound doesn't depend on n. Okay, so if you have a polynomial of with one variable, the probability that you hit the root is still less than the d2 over m. Okay, m is very large, d is bounded, then you're in business. Okay, and what I want to convince you is that the probability that this is true is precisely the probability that I hit the roots when I take the random value r in this polynomial. Okay, so think about this. Imagine that I get, you give me a polynomial, so you give me the pi, and you pass this test. Okay? So all these things are correct, and now what is the probability that if there was an error, now b would be correct? Okay, well, it's a probability that a certain polynomial, maybe not this one, but this one minus b equals 0. It's the probability that I hit the root of that one. But that one, we've seen, the degree is bounded by n squared. Okay, and p, which is this Schwarzschild m, is of the order of 2 to the 2n. Okay, so essentially the probability for us, it's n squared over 2 to the 2, n squared over 2 to the 2n, and this is smaller than any epsilon you want. Okay, so therefore the probability of the converse is bigger than 1. Well, you can see n squared over p. Okay, n squared p. This is about p. Okay, so let's go back to the whole story here. So the whole story is we linearize, we want to reduce to one pair matrix value, and we want to propagate the error if there is an error. So we have to show that if there is an error, it will propagate. And in this lemma, we show that it propagates with probability 1 minus n squared over p, which is minus epsilon. So it's certainly the probability that it doesn't occur is, less than 1/2. So eventually everything will go back, will go fine. And if there is an error, it will be caught in this protocol, and the protocol will reject with high probabilities. Okay? If you want to remember one thing, remember this bound, if you have a polynomial, so usually that's why people love polynomials of low degree. Because if they have polynomial of low degrees, if they have a large enough domain, they hit values randomly, then most likely they don't hit the roots. And therefore, they can use this to do a lot of interesting things. Okay, you can use this to your advantage. Okay, so which is precisely what you do here. Okay, so in the end, if you put these two lemmas together, then you're able to conclude that, okay, so the theorem will be that take the language of the permanent. So permanent is a set of pair AA with A equal the permanent big A. Okay. Now, there exists a honest prover such that PV on the input X equals 1. Okay, so because it's true with probability 1, I write it like this. And then second, for all P prime, the probability that P prime V accept is actually smaller than, so here it will be smaller than epsilon. So here the probability that I reject is bigger than this, so the probability that I accept is smaller than epsilon. Epsilon is this quantity. And which is, so it implies, I mean, it satisfies the, it's actually even stronger, the condition of the interactive proof. So here is the protocol for the permanent. Okay? So, key idea, reduction, many problems to one problem, okay, by linearization. And linearization is treated with a polynomial of low degree, and low degree polynomial with random, values. You can check if they are, is 0 or not very quickly. Okay, so traditionally in a class on interactive proofs, what people do is now they generalize this protocol to QBF. So QBF is these quantified Boolean formulas, and there is a two-step process. You transform the logical formulas into polynomials, and then you apply this. Okay, so it's done in the notes. If you're interested in this, I think you should have a look. And but I don't think it's it's pretty much the same spirit. So we're not going to learn many new ideas. So now let's go back to what I said before about computing with errors, because that's kind of ideas that may be counterintuitive. Okay, so what is counterintuitive is the following thing. So here is the variation on the theme. Okay, not only I can verify something, but maybe I can also compute, and in a non-trivial way. Okay, so here is my problem. Imagine I have an arithmetical function, so of many variables, x, y, z, and I define it by what when people call arithmetical operation, they mean multiplication, division, addition, subtraction. Okay, so let's see, x squared divided by y plus z minus 2xz. Okay, random arithmetical operations. Okay, now imagine the following situation. So here you're going to use, here you have multiplication, here you have addition, here you have multiplication, here you have divisions. Okay? So you're going to use 4 processors. One for subtraction, one for addition, one for multiplication, one for division. Okay? Now imagine that you're working on a domain like this. of size m minus 1. When you hit m, you go modulo, and then you know, it makes simplify. So let's suppose we're in the area of say 0 up to 99. When I hit 100, I'm back to 0. Okay, that is my domain. All right. So in this domain, for example, I add 17 plus 5. Okay. Now, when it's correct, I get 22. Okay. But let's suppose I make 30% of error. Everything works with error. Well, let's suppose we make 30% of error. So when you do this, when you get 75. Okay? Why not? What is the probability to get something crazy? 1/3. Okay? All right. But it's crazy here, it's crazy there, it's crazy everywhere. All right? And now you say, no problem. Okay? It's like saying, okay, I'm sure you work with Windows and all these things, and sometimes they bug, of course, right? There's no problem. All you need to do is a process by which, using buggy components, you eventually get a very reliable system. Right? So let's concentrate, and of course it's entirely possible to do it, and how to do it is let's concentrate on the division, because it's the simplest to figure out. Okay, so imagine you take, so when you divide x by y, actually you get two parameters. You get a quotient and a rest. Right? And the equation, I suppose, is x is equal to y times q plus r, and r is smaller than y. Right? This is the definition of the division. Sorry?
I think R is smaller than
R, the rest is smaller than the divider. Okay? All right. So you divide 17 by 4. Okay? So if you're correct, you should get 4 as a quotient and 1 as a rest. Okay? Well, just imagine I concentrate on the quotient for a minute. Okay? I want to okay, so just imagine now your division give me a quotient with 30% error. Okay? Now, how do I kill the error?
Do it a bunch of times. If I do it 100 of times, then I simply look at the most frequent value.
But the division is not probabilistic. You divide 17 by 4, you get 25. If you get 25, you divide 17 by 4 again, you get 25 again. Okay? Okay. Probabilistically means when you take random x and y in the domain, the probability that you get something crazy is 30%. It's not the fact that these are probabilistic computations. Okay? Actually, they are not. If you concentrate on some error, numerical errors, you do it again and you get the same error. I mean, on most machines. sometimes you don't do it. But okay, you understand the model, and it's a model which is not, not far from the real thing. Okay, so in other words, this is correct. Okay, now divide 20 by 5. I look at the quotient only. Now I get 17. Wow, this is crazy. Okay. Okay, so the question is, okay, how do you do it so that you kill the craziness
Add something random.
Yeah, but where? Obviously you have to use something random, but where?
I would add to the nomination.
To the where?
To the upper part. For example, like I would put add 5 and test again.
You add a random value to 20?
Yeah. 5 times k, for example, where k is random.
So you multiply
No, 20 plus 5 times k.
20. So you instead of you want to do this, and you're going to do 20 plus some random values, or
Yeah.
and then you divide by what?
By 5. Like by 5.
Divided whole thing.
Whole thing by 5.
Okay, and after that minus 1. Minus error.
We're getting closer. We're getting closer. It's not quite this that you have to do, but something like this, yes. Okay, so what you have to do, something much simpler. What you have to do is take a random value, exactly what you said, but you multiply numerator and denominator by the same value. Okay? So in other words, you take r equal 3, for example. Okay? So this time you're going to divide 60 by 50. Okay? And of course, you should get the same value. If everything is correct, you should always get the same quotient. Okay? But we're in a crazy situation where you know, everything could be crazy. So if I do this algorithm, so essentially you only define x by y, you're looking at the quotient q. Okay, but my operator is buggy. So what am I going to do? I'm going to define xi is equal to x times r sub I. Y sub I is y times r sub I. And then I divide xi by y sub I. And I get some q sub I. Okay? And I'm going to repeat this a certain number of times. Well, how many times you're going to repeat this? Well, I propose something like 2k plus 1 times. Why 2k plus 1? Because it's an odd number. And I'm going to look at a majority consistent answer. In other words, so the answer here should be 4. Okay, so what you're going to see is, let's imagine you enumerate q1, q sub 2k plus 1. Okay, so what are you going to get? Well, you're going to get 17, 4, 65, 4, 4, 4. 1, 2, 3, 4, 5, 6, 5, 7. 7 is odd, right? But you can see that one of the value appear k times, or k plus 1 times, okay? Which is a majority answer. Okay, so the answer is 4. If I don't have a majority answer, I keep flipping coins, okay? And you can see, okay, if you have basic knowledge in probabilities, that with high probability, when k doesn't grow very much, there will be a majority answer, and it will be correct with error probability as small as you want. So if you want, for example, epsilon to be 10 to the minus 10, then if you do the computation, maybe you're going to get k equal 15, something like this. So you're going to go for a majority solution at step 31 with 16 consistent answers. And you should get one with probability 10 to the minus 10, and this will be correct. Everybody understands what's going on here?
Why we should have probabilistic error in computation, but shouldn't we just implement error and throw out randomness? Will this work for us?
Where should we? I didn't get you.
You said that error I in xi, yi is random.
Yes.
You flipping coin to that.
I flip coins uniformly on my domain. This is important. Okay. The probability to get the value I is 1 over m. Okay, that's important. Okay, because Okay, it could be that the errors are concentrated in some corners, and I don't see it. Okay, and you want to catch even though you have errors in the corner, you want to catch them with, sufficient probabilities, and this will do. Okay?
Then you should suppose that your errors cannot concentrate along the line. Because,
no, they could if you random.
Because you can fight against the corner arrays, but you cannot fight against the arrays along this line.
Yeah, but
if all of your errors are along the line,
what you have to realize is that if R sub I is uniform in the domain, then so is Y sub I. Y sub I is also uniform. It's not totally obvious to see. Okay, because of the modulo that distributes exactly the way you expect it.
Yes, but if all your errors are concerned about the situation when you get the answer 4, or say 30% of all answers are calculated erroneously. So all pairs which should give that answer 4 give a crazy answer.
Yeah, but see, when I say you have 30% of errors, it means that the errors distribute uniformly. It means that when I take X and Y randomly, what is the probability that I get the wrong answer? Now, is it possible that it would concentrate on one particular value as you suggest? I don't think so, because if you concentrate on one value, yes, sir. I understand. Okay. You can think that where does the 30% come from? Okay. In other words, does it make a big difference if I go from 30% to 40%?
No.
It makes zero difference. Does it make a difference if I go from 40% to 49.9%? It makes no difference.
Yes.
The main difference is if I cross the line from 49.9 to 50%. By the time I cross the line to 50%, this is wrong. This is not correct. That you will, if you want an error 10 to the minus 10, you will have such a small bound on the k. Okay? You will still have a bound on the k, but it will be not as good. Okay? And not realistic. Okay? So, all of this to say that if you extrapolate this technique from the quotient to the rest, from the addition to the multiplication, so on and so forth, you give me this function. Each of the processor is buggy. I don't care. I'm going to multiply. Okay, on the quotient I will do this, but on the subtraction I will do something slightly different. And I will take a majority answers, and the majority answers will kill the error. All right? So, okay, so this is, of course, a slight deviation from the previous techniques. But nevertheless, you have to be aware that often it's, when you look at these probabilistic techniques, it's also a technique to correct, okay, once you compute with buggy systems. So now, of course, people designing Windows, they love this sort of thing, right? Because they know that these programs bug once in a while, but then, provided you randomize at the right places, then they don't bug with high probabilities. Okay?
Probably for this thing to work, you need to assume that your uniform distribution is more strong than you suppose. That you should have uniform distribution of 30% error of all pairs and also on conditional probabilities. If you fix one, then you have 30% errors for if you fix X, you have 30% error on all Y's. and if you fix y, you have 30% of errors on all axes. And under this assumption, this works.
I understand what you're saying. I'm not sure you need this. I'm not sure you need this because you never go from an x-y pair to an x-y prime pair, where y prime is only dependent on y with the randomness. You always go from an x-y pair to an x prime y prime pair, where the randomness is applied to both. Okay, and therefore the fact that you need the conditional distribution to also be within 30%, I'm not sure. No, you ask a good question, but I'm not sure you really need this. But maybe you need it for the addition. Once you try to make the addition robust, maybe at that point you need some conditional revision. And it's entirely possible. Okay. Now we'll see that the linear test, to essentially the addition, is something that we will use again. So if you have, for example, just imagine you have the function and then it's a linear function, so it's ax plus by. So when I talk about linear function, this is it, right? And now imagine that you have a function and you do the following test. You take xy random, then you take x prime, y prime random, and you check if you want to check if x, y plus f x prime y prime is equal to f of x plus x prime, y plus y prime. Okay, when you have a linear function, okay, it satisfies this. Right? So you don't know ax plus by. You don't know a neither b. Okay? You have an oracle. I give you xy. You give me a value. Okay? Now I want to test: are you linear functions or not? Okay? But what you can, and obviously you're going to take x and y random, x prime y prime random, and check this. Okay? Is this going to be good? First question. And second question, could you eventually correct the function? In other words, if the function was epsilon close to be linear, could you get a correction? Do exactly what we were doing before. So this is going to come up as an example of property testing. So this is a typical example of property testing, where you use the most natural distance between two functions. So what's the distance between? We're supposing that we are on a domain always like this, right? So what is the distance between f and g? No, it's not what you have in mind. No. This will be, of course, some norm on the value of the function, but it's not exactly the value of the function. You want to compare, are the function different or not? See, it's more like...
Maybe some of the absolute values divided by f.
You want to say what?
Some of all absolute values of the differences divided by f. So you calculate f minus, the function f minus g, and
yes.
take an integral or sum divided by n.
Yes, you could do that. You could do that, but you could also Yes, it could do that. But you could, I mean, the first thing that comes in mind is the number of x such that f of x is different from g of x. And you divide by the size of the domain, m. You see? You have two functions, okay? What's the distance between the two? Is essentially the number of points where they get different values, okay? Which
this is a sort of Hamming distance.
it's like a Hamming distance, exactly. What you want to compare is some distances on the value of f of x, which would be something else. But here, remember, you have to think of, f. You have a function maybe like this, and g is a function like this. All right. Okay, so question, is g close or far from a linear function? Okay, so we have a property of function, which is the linearity. So this is a set of functions that are linear. My problem is, I want to decide, is f is linear or is f very far from linear? And if it's close to being linear, I want to correct it. In other words, I want to get this function, the straight function. Okay? So that's exactly the connection with property testing in case of linear function. Okay, but with this distance. Okay? And maybe we'll see this because at some point it's entirely feasible. So first of all, the test is this. Exactly. Do this test. Okay? So take random x, random y, random x prime, random y prime, and see if you have this. So if you hit one point where you don't have this, you reject. Okay? And you want to show that if f is far from a linear function, I will reject with high probability. And if I accept, f will be close to a linear function, and not only I can test, but I can correct. In other words, if this function is like this, then I will get automatically this linear function that does the correction. Okay? Now doing the correction is pretty much what we were doing before. Okay? So this I show you the loop via a different path between property testing and correction somehow. Okay? Very useful thing. Okay? And it's always the idea that if you have linear functions, if the functions are almost linear, that's good enough. Okay, you can correct. Okay, so it's not a totally obvious thing, but you can correct. All right, so now I have 10 more minutes. Yes? So I want to introduce the framework that we'll use tomorrow. So the framework is this PCP, and usually it's parameterized by two functions, R of n and Q of n. Okay, so here is the idea that you get a proof, which is a sequence of bits, which is a witness for a problem. In our case, it would be the value of the permanent. Okay, and then you have a prover. You have a verifier that uses random bits. From these random bits, he gets some random positions. He gets the value, and from that, he asks himself, is it enough to verify if it's correct? Okay? All right. So now, these functions R of n, so here is the number of random bits. Okay, so remember that we have an instance x, which is of size n. Okay? So imagine we have a SAT instance, set of clauses, okay? And you want to convince me that they're satisfiable. So you're giving me a proof, a witness, and I'm going to sample in how many positions? Q sub n. So number of queries, so this is called a query, is a Q sub n. Well, usually it's in O notation. So random of, it's also O of Rn. Okay, so that's a model. And now what is the equivalent of this condition here? Okay, so that's where I'm going to define. So let's make sure I use the same notation. Yeah, so essentially the verifier, you have to think of the verifier as producing the position, I call them so he's going to produce I1, I sub q. Okay, these are the positions here. And then he will get as an answer R of I1, R of IQ. Okay, this is the bit here. Okay, so if this is the position is I1 here, the value is 0, 1 is R of I1. This is what I read. I only read one bit, okay? And then I have a function f that takes the input, take the random bit, take the values that I get here, so R of I1, R of IQ, and give me a value which is either 0 or 1. Okay? If it's 0, I reject. Okay? So if f, and I write v of x rho, well, okay, pi is the sequence here, the witness, equals 0, well, equal 1, if and only if this value is 1. Okay, so the notation, before we're using the notation PVX equal 1. Okay, so instead of using PVX equal 1, now I use, there is no interaction, so the verifier is a unique function that takes random bit, okay, the input, what he read on the pi, and now you want the condition to be the equivalent of the condition here. It's going to be the following thing, which is almost the same. So this is a key definition. So you'll say language L is in PCP Rn Q sub n if there is a polynomial, a poly verifier such that, okay, so here I replace the prover by pi. Okay, and I replace the PVX by this. So V sub x rho pi. or 1. Okay, so in other words, I want the verifier to accept all the times. If X is nil, there must be a proof such that I accept all the times. And if I'm not in the language, then any proof should not convince me with more than 1/2 probability. So therefore, V X rho pi prime. Okay? So you can see that essentially I'm keeping the same structure. Okay? Condition here is exactly the same. All I change is that the exists prover is changed by the exists proof, and for all prover is changed by for all proofs. Okay? Condition is kept exactly the same. And in property testing, it would be kept exactly the same as well. Okay? So now the question is, how do I design? I mean, is it possible that I can reduce the number of queries to the minimum possible? So the challenge here is to reduce Q sub n to some constant, okay? And that's what so what we will show is that tomorrow, that essentially NP is the same as PCP n cube 1. So in other words, you need constant number of queries. Okay? So number of queries on pi is independent of n. Maybe 17 if you want. Okay? So in other words, you give me a proof, and I sample the proof on finitely many points, okay, and I check if there is an error. It's totally counterintuitive, because if you think of SAT, for example, okay, I give you a valuation, I could lie on one value, say x5 should be 1, I tell you 0 to see if you see it, right? Well, if there is one error and you sample, you never see it. One error somewhere, you never see it. So you have somehow to propagate the error everywhere, if there is an error, exactly as we propagated the error here. Okay? So that's what I'll show you tomorrow. On SAT, how you get a pi, which is actually such that you can sample it, and if there is an error, you see it with high probability. Okay? And after that, you really understand that sampling, if you know what you're doing, gives you tremendous power, because not only you can decide, but you can correct, you can do all of incredible things that are totally counterintuitive. Okay? So probably a good time to stop here.